Hello, Cal 2. We're doing some homework. If you're watching this, this is being recorded in summer of 2020 during coronavirus social isolation. And I'm doing the odds from what's in my homework set now. There's a good chance I've changed the homework set some between this year and whatever year you're watching this, if you're not watching it in 2020. I'm doing what were the odds back then, but if I've added problems, then maybe this is all off. Let's do a u substitution. U equals 3x minus 2. So x is 1/3 u plus 2. dx is 1/3 du. What's this integral turn into? This turns into the integral of over u to the 1/2. 1/3 du is our new dx. 2x minus 4 becomes 2/3 u plus 2 minus 4. I got fractions inside fractions. I like doing the multiply the top and bottom by 3/3 trick so that I don't have fractions inside of fractions anymore. Now I have 2u plus 2 plus multiply that 3 onto that 4 and I get 12. A 1/3 and a 1/3 makes a 1/9 I can pull all the way out over u to the 1/2. This is 1/9 integral of 2u plus 4 minus 12 is minus 8 over u to the 1/2. Split up the fraction. 1/9 integral 2u to the 1/2. No, don't do that. 2u to the 1/2 minus 8u to the negative 1/2 du. This is 1/9 of... Actually, let's push the 1/9 in. Erase? Are you crashing already? Okay. 2/9 of u to the 1/2 plus 1 is u to the 3/2. I get a 2/3 out front. Minus 8/9 times u to the positive 1/2 divided by 1/2, that's a 2 out front. Plus a constant. Equals 4 over 27. What's u? U is 3x minus 2. 3x minus 2 to the 3/2 minus 16 over 9. 3x minus 2 to the 1/2 plus c. Cool. I got a definite integral that wants a substitution. Hey, if you've already gotten through the integration by parts section, it's worth noticing this is also a good candidate for the tabular method. Take the derivative of this enough times and it'll be 0, and this thing is a baby substitution of just a power function, so you can integrate it an indefinite number of times. I'm going to do the substitution instead because I put this under the substitution section. U is 2 plus x, x is u minus 2, dx is du. And in particular, the point of this problem is the bounds of integration are going to change. X is 0 becomes u is 2. X is 3 becomes u is 5. We're integrating from 2 to 5. Of x squared becomes u minus 2 squared. Square root of 2 plus x becomes u. dx is du. I gotta FOIL that out. U squared minus 2, 4u plus 4. U to the 1/2. Push in the power of a half. I get u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2 du. I don't have to convert back to x's because this one's a definite integral. I get u to the 7/2 times 2/7. This one's u to the 5/2 times 2/5. With the 4 makes that 8/5. This is u to the 3/2, puts a 2/3 out front. With the 4 makes it an 8/3. I need to evaluate that from 2 to 5. gross. I get 2/7, 5 to the 7/2 minus 8/5, 5 to the 5/2 plus 8/3, 5 to the 3/2 minus 2/7 times 2 to the 7/2 plus 8/5, 2 to the 5/2 minus 8/3, 2 to the 3/2. And an exam, just put a box around this. Don't try and deal with this. You could get digits if you wanted to. Although I guess if all you wanted was digits, you could ask your calculator to do this definite integral. But these things are factorable. The key thing is there's a 5 to the 1/2 you can factor out of that whole thing. You factor that 5 to the 1/2 and you get a rational number that you can actually deal with. Minus, you can factor a 2 to the 1/2 out of this thing. We got some multiple of root 5 minus or plus some multiple of root 2. I factor out this root 5. What am I left with? I'm left with 5 to the 6/2. 6/2 is 3. Minus 8/5. 5 to the 2/2. 4/2 is 2. Plus 8/3. 5 to the 1/2. That's called 5. This gives me 2 cubed minus 8/5. I'm factoring out that negative. 2 to the 2. Plus 8/3, 2. What is this? 125. God, I got a common denominator of 15. I get root 5 times, what's 125 times 15? Can I do that? 125 times 5 is 625. Times 3 is 1875 over 15. This is 25 times 8 is 200, times 3 is 600 over 15. This is 40 over 3 times 5 is 200 over 15. This one is root 2 times, again, a common denominator of 15. 8 times 15 is... That's 30 times 4, that's 120 over 15. No, it's not 120. I think that's wrong. 8 times 15, 80, and 40 is 120? Yes, okay. Minus, this will be 4 times 8 is 32 over 15. Times 3 is 96 over 15. 16 times 5 is 80 over 15. This is going to be 1475 over 15. That reduces. I didn't need 15 as a common denominator. The 5 would have canceled there. I could have done this with thirds. Well, 1475, let's reduce this by 5. I get 295. 295 over 3. You better not be divisible by 3. You are not. Okay. How many is this? Yeah, there's no reducing here. 120 plus 80 is going to be 200 minus 96. I'm getting 104 over 15 root 2. Here's our weird answer. That was number 3. And heads up, you don't have to do that kind of gross simplifying. If you get something like that on the exam, don't try and do all that junk. Exam time's too valuable. It's worth doing that stuff in the homework. That's what homework's for, is doing hard problems. This is begging to be done by parts. Integral u dv is uv minus integral v du. Hey, my stream's going, right? Looks like it. Okay. I want u to be t, dv is going to be e to the negative 3t dt. So du is dt. V is the integral of that is negative 1/3 e to the negative 3t, no dt. So this equals uv is negative 1/3 t e to the negative 3t minus the integral of v du is negative 1/3 t e to the negative 3t dt. Nope, the t's not... I did that wrong. v du is this times this. I was looking at the t. Minus negative 1/3 e to the negative 3t dt. There's a thing in integration by parts where very often this integral turns out to also be the integral you do right here. I'm getting negative 1/3 t e to the negative 3t minus 1/9 e to the negative 3t plus a constant. That's not where my homework is. It's number 7. This is the thing where you do parts twice and you get back to where you were. I'm going to let u be e to the 2 theta, dv be cosine 3 theta, d theta. So du will be 2 e to the 2 theta, d theta. V will be integral of that is integral of cosine is sine. Divide by 3. The original integral equals uv is 1/3 e to the 2 theta sine 3 theta minus the integral of v du is 2/3. I'm going to push the minus inside and make it negative 2/3 inside e to the 2 theta sine 3 theta d theta. I'm going to do parts again, and I want to make sure I keep going in the same order. This e to the came from being du last time, so I want to make that still be u. U is going to be negative 2/3 e to the 2 theta. dv is going to be everything else. It's sine 3 theta d theta. So du is the derivative of this, is negative 4/3 e to the 2 theta. V is going to be the integral of this. It's going to be 1/3 cosine 3 theta negative. Yes. You've got a d theta on you. We get that thing plus uv is 2/9 e to the 2 theta cosine 3 theta minus the integral of v du is minus minus minus. This is a negative. 4/3 times 1/3 is 4/9 e to the 2 theta cosine 3 theta d theta. Hey, what do you know? This is our original integral. Oh, I guess I should fill in this part since this is the line I'm doing. One plus 4/9 is 13/9 of our integral equals that plus that thing. So our integral is that times 9 over 13. 1/3 of 9 over 13 is 3 over 13. E to the 2 theta sine 3 theta plus 2/9 times 9 over 13 is 2 over 13. E to the 2 theta cosine 3 theta plus a constant. I think it's worth taking the derivative of this and seeing what little weird miracle happens to make the derivative of this be this. Both of these need the product rule. This guy's going to spit out an e to the and a sine and an e to the and a cosine. This one's going to spit out an e to the and a cosine and an e to the and a sine. And the numbers 3 over 13 and 2 over 13 just happen to be the correct numbers so that all the sine ones cancel out and all the cosine ones add up to 1. If you get a handle on this kind of problem, it's pretty reasonable to say, hey, I know the answer is going to be some constant multiple of e to the 2 theta sine 3 theta plus some other constant multiple of e to the 2 theta cosine 3 theta. And taking the derivative of this and then solving for a and b is a pretty reasonable way to get the solution to this without integrating by parts. But, you know, you have to learn integration by parts, so you might as well get the hang of this trick. We got, here's number 9. When you have a natural log, it loves to be the u in the parts. We're going to do parts and let u be natural log w. dv is everything else, is w to the 1/2 dw. du is 1 over w dw. v is the integral of that, is w to the 3/2 with the 2/3 on it. This becomes uv is 2/3 natural log w w to the 3/2 minus the integral of v du is 2/3 1 over w w to the 3/2 dw. I see so many students who integrate this now and get natural log and integrate this and get w to the 5/2, and you can't do that. The whole reason we have integral by parts is the product rule is not as simple as derivative of the one times the derivative of the other. If it was, we wouldn't need a integration by parts in the first place. But this is doable because I can smush those two things together. 1 over w times w to the 3/2 is w to the 1/2. And I can integrate that. Integral of w to the 1/2 is going to be w to the 3/2. Stick out an extra 2/3 times 2/3 is 4/9. There's that part. I get 2/3 natural log w times w to the 3/2 minus that thing plus a constant. You should be clearly not part of the same thing. There's number 9. How far are we going? Oh geez, we're going to be here for a while. What did I just did? It was this W one. Let's do this 11 one. X cosecant squared. I guess this wants parts. Yeah, the x seems ready to get differentiated. Let's say u be x, and let's dv be cosecant squared. I'm anxious that, am I going to be able to integrate this? And then I relax when I remember, oh yeah, this is just the derivative of cotangent. Wait, no it's not, because the derivative of cotangent would be negative cosecant squared. So the integral of this is negative cotangent. Meanwhile, du is 1 dx. This becomes negative x cotangent x minus the integral of v du is negative integral cotangent x. How do I integrate cotangent? Well, it's cosine over sine. This is begging for the u substitution, u equals sine x, because du is going to be the cosine x dx. This turns into the integral of 1 over u du is natural log absolute value u. I'm ready to write down the answer. It's negative x cotangent x plus natural log absolute value. What was u? U was sine x plus a constant. (13) 0 to pi x sine x cosine x. I can't tell, should I be doing this my favorite way to do this problem, or the most standard way to do the problem? I like knowing the fact that sine 2x is 2 sine x cosine x. sine x cosine x. This is like a version of the product to sum thing, but I mean, well, this is the double angle identity for sine, but just like with product to sum, you can take a product of sines and cosines and turn them into a sum of a sine and a cosine. If you did that here, you would get the single sine 2x, but you don't need to memorize the whole product to sum to know the double angle formula for a sine. So this can become x times a simple trig function of sine 2x. Is that the right way to do this, though? It's certainly easier than doing a parts without that. Doing parts without that would bank on me looking at sine cosine and hopefully being able to integrate it. So I can look at it and say u equals x, dv is sine x cosine x. And now I'm asking myself, how hard is that to integrate? It's not that hard. You can let u be sine x, and there's an easy trig substitution. It's 1/2 sine squared. I guess that's the thing to do. Yeah, let's do that. The alternative, which might be useful... Actually, let's do the alternative. If I didn't know how to integrate this, or if I decided, hey, doing a substitution in the middle of a parts problem is a sign that you're going about it the wrong way, which is often the case, just let u soak up a little more stuff. Let's try what happens if I let u be x sine x and dv is cosine x. What's going to happen if we do this? Du is the derivative of this, is 1 sine x plus x cosine x, all dx. V is going to be the integral of this, is just sine x. So this becomes uv is x sine squared x evaluated from 0 to pi. Hey, luckily that's 0. Sine is 0 at 0 and pi. This goes away. Minus the integral of v du. V is sine x. Du is sine x plus x cosine x dx. I get minus the integral of 0 to pi sine squared x dx minus the integral from 0 to pi of x sine x cosine x dx. Hey, miracle of miracles, this is the original problem. So 2 times that original integral is negative integral 0 to pi of sine squared. How do you integrate sine squared? I don't know if you've seen this yet, but in the trig trick section we learned the power reducing formula. This is 1 minus cosine 2x over 2 dx. So our integral that we want is going to be negative 1/4 integral from 0 to pi of the integral of 1 is x minus the integral of cosine 2x is going to be sine 2x. Divide that by 2. Still need to evaluate from 0 to pi. Plug in pi, and I get pi minus 0. Plug in 0, I get 0 minus 0. Or I guess that one's a plus. I'm getting negative pi over 4. That feels wrong, because is this going to be negative between 0 and pi? What does this look like? It's surprising for this integral to be negative to me. What is x? Maybe it shouldn't be. Sine and cosine are negative sometimes. Sine x... Man, I got some hiccups. Oh. If it sounds like I'm burping, I'm probably hiccuping. Let's just graph that from 0 to pi. Positive. Negative. Oh, it's negative more time than it's positive. Yeah, we should get a negative. Cool. Oh. I guess as long as I got the thing graphed, I might as well ask my calculator to tell me what the integral is. I need to make the window a little bit further than... I'm still suspicious of this number. Hey calculator, please calculate the integral from 0 to pi pi over 4 is a little bigger than 3/4. This makes sense. Cool. Cool beans. Cool those beans down. That was number 13. Here's 15. Oh. Man, I was telling my class I need to add some things that have the integral of sine squared or cosine squared, because those weren't obviously there. Well, they're there, but they're hidden. This is begging for the u substitution u equals 1 over t, because du is negative t to the negative 2 is negative 1 over t squared is right there. I'll stick a negative here and a negative here. This becomes negative integral sine squared u du. How do you integrate sine squared u? It's negative integral 1/2 minus cosine 2u over 2 du. It's negative u over 2. Integral of cosine 2u will be sine 2u over now 4. With that negative and that negative, it's going to be positive. What was u? U was 1 over t. Negative 1 over 2t plus sine 2 over t over 4 plus a constant. That was 15. Number 17. Okay. In my head, I'm remembering that secant cubed is the hard integral. Life is hard if I have an odd number of secants and an even number of tangents. Well, I have an even number of tangents, rut-row, but I have an even number of secants is good news. That's the little push I need to get me going of, wait, why is that good news? It must be good because an even lets me pull off 2. I'm going to pull out 2 secant squared thetas, or 2 thetas, 2 secants in the form of secant squared are getting factored out over here. Setting them off to the side is helping me notice the substitution that's going to be useful. The useful substitution is going to be u equals the thing whose derivative is secant squared. What is that? Oh yeah, that's tangent. I want u to be tangent theta, because then du can be secant squared theta, and hey look, I have a secant squared sitting over there. This is fine, that's going to be u to the 6th, but what am I going to do about this guy? Well, that guy's going to be handled because he is secant squared squared, and what's secant squared? Secant squared is tangent squared plus 1. I gotta check this out. I screw this up so often. Every time I don't write this out, I screw this up. Tangent squared plus 1 equals secant squared. Yes, okay. Tangent squared plus 1 squared times tangent to the 6 times secant squared theta d theta. Okay, this is now ready for an easy peasy substitution. Those are theta values from 0 to 2 pi. I need to change those into u values when I change this integral. What's tangent 0? It is 0. What's tangent pi over 2? Is tangent undefined at pi over 2? Oh, that's not pi over 2, that's pi over 4. That's good. It wasn't time for me to put improper integrals on here. It's doable at pi over 4. But it becomes the thing you have to rewrite it as a limit as it goes to infinity. What's tangent pi over 4? It's 1. Oh, that's nice and easy. Tangent squared plus 1 squared becomes u squared plus 1 squared u to the 6 du. Let's square that. That's u to the 4th plus 2u squared plus 1 u to the 6 du. This becomes integral 0 to 1 u to the 10 plus 2u to the 8 plus u to the 6. I can evaluate that integral. I get 1/11th u to the 11 plus 2/9 u to the 9 plus 1/7 u to the 7. Evaluate that from 0 to 1. Plug in 0, you get 0. Plug in 1, you get 1/11th plus 2/9 plus 1/9 minus plug in 0, you get 0. I said that really quickly. Get in the habit of actually checking that when you plug in 0, you get 0. Cosine 0 is not 0. E to the 0 is not 0. There are many functions where when you plug in 0, you don't get 0. So make sure you're actually checking this. I'm doing it fast, but I am actually thinking about that. I wrote 1/9, but that was supposed to have been a 7th. Do I find a common denominator here? I'm just going to write what the common denominator is. The common denominator is going to be 7 times 9 times 11, whatever that is. I get 9 times 7 is 63 of this. 2 times 11 times 7 is 154 is what goes here. 9 times 11 is 99 is what goes here. 217, 316, I think this is 316 over 7 times 9 times 11. Can I do that? Oh, 9 times 11 is 99. Times 7 is going to be 700 minus 7 will be 693. I think that's the number. Don't stress too much over adding fractions. It's not a good idea. On the exam, it's totally reasonable to put a box around this. I am not giving you an exam over can you add fractions. I'm going to do it because this is a homework context. It's not a contest. I'm grading you. I guess it kind of is a contest. 17. 19. Cotangent cubed. How do you integrate cotangent cubed? Not you. Should I? Let's close that. I got too many windows open. This stupid thing. Close that, close that. Don't need that, don't need that, don't need that. Okay, that's a little cleaner. No, why are you still? I just closed you. Okay, copy. Let's integrate cotangent cubed. How do you do cotangent cubed? Secant cubed is hard because there's an odd number of secants and an even number of tangents. This one should be easier for having an odd number of tangents. Is that easier? The reason it's easier is because you can pull off a tangent and a secant. I don't have my secant to pull off, but I'm going to pull one off anyway. Okay, so this is going to be cotangent cubed x. I wish I had an extra secant to pull out. Well, I can pull out an extra cosecant x if I put a cosecant x down here. I'm pulling out one of the cotangents. Have I done this right? This thing, cotangent cubed, cosecant cancels cosecant. Cool. So writing it like this is allegedly going to make it look easier to suggest the substitution. Pulling out that cotangent cosecant makes me think about the substitution u equals negative cosecant. That's the thing whose derivative is negative cosecant cotangent. I want u to be cosecant. Du will be negative cosecant x cotangent x. Okay, that's good. Cosecant is my u. Is this all in terms of u? Not right now, but I can fix those cotangent squareds. If I don't know the secant tangent version, I definitely don't know the cosecant cotangent version off the top of my head. Divide both sides by sine squared. I get 1 plus cotangent squared equals cosecant squared. Cotangent squared can be rewritten as cosecant squared minus 1. Okay, now this is going to be an easy substitution into a doable integral. I still have the negative out here. I get negative integral u squared minus 1 over u du. Split that into separate fractions. Integral of negative u plus 1 over u. I get negative half u squared plus natural log absolute value u, and u was cosecant. Negative half cosecant squared x plus natural log absolute value cosecant x plus a constant. Oof. Not you. Did I close the... I closed the stupid thing, didn't I? This is Technic Center. This is where mathematicians write up their math. I don't need a tip. Let's open homework 1. This is how you type up math. This is the integral of a fraction. The top of the fraction is x minus 7. The bottom of the fraction is that. Put a little space, dx. Show me a PDF. And then I don't need you open anymore. Cool. What was the last one I just did? It was 19. Here's 21. Sine secant to the 5th. We spent a lot of time talking about how to do a power of secant and a power of tangent. We spent a lot of time talking about how to do a power of sine and a power of cosine. We didn't talk about mixing sines and secants. Let's try just turning this into sines and cosines and see what we get. This is sine x over cosine x to the 5th. I guess it's really natural to split this into a secant. Sine over cosine is a tangent. And then I'm left with 4 cosines on bottom. Those are 4 secants. That's an even power of secant. That's an easy one. That should be doable. But this version is also pretty doable, because if I let u be cosine x, I have that du sitting up there. Du is going to be negative sine x dx. Negative, negative. This becomes the integral of negative u to the negative 5. That'll be u to the negative 4. Put a negative 1/4. The negative cancels with the negative that's there. 1/4 u to the negative 4 plus a constant. And what was u? U was cosine. This is 1/4. Is this secant to the 4th? Yeah. It's cosine to the negative 4. That's secant to the 4. Oh yeah, because the derivative will be secant cubed times secant tangent. I see secant cubed, and then a secant. And then the last one, secant sine makes a tangent. Yeah, that's the right answer. What's 23? Integrating 1 over cosine minus 1. This is that stupid trick. All the trig tricks feel stupid. But they let you integrate functions that actually show up all the time, so, you know, they're super useful, despite feeling like stupid tricks. When you see cosine plus 1, cosine minus 1, sine plus 1, sine minus 1, 1 minus sine, all versions of that, those are factors of 1 minus sine squared or 1 minus cosine squared. I'm going to multiply by cosine plus 1 on top and bottom. I'm multiplying by 1, so I'm not changing anything. On top I get cosine x plus 1. On bottom I get cosine squared minus 1. That's the opposite of 1 minus cosine squared. That's the opposite of sine squared. Let's split this into separate fractions. Actually, let's split it all the way into separate integrals. The second fraction will be 1 over sine squared. That'll be cosecant squared. Perfect, I know the integral of that. The integral of cosecant, negative cosecant squared is cotangent x. This one's begging for the substitution u equals sine x. Du will be cosine x dx. So we're integrating negative 1 over u squared. That's 1 over u. Yeah, derivative of u to the negative 1 is negative 1 over u squared. So the integral will be 1 over sine. It'll be cosecant. That's a suspiciously simple answer. Derivative of cosecant plus cotangent is 1 over cosine minus 1. Weird. 25. We're in trig substitution land. There be monsters here. Whenever I see a trig substitution, I'm going to check and make sure this isn't doable by a simpler u substitution. If I had an extra x out top, then I would have the derivative of x squared minus 1, basically, and I'd be ready to do that. I don't have that, so I probably need to actually do the trig substitution. Let's let u be, what is it here? This one is secant theta. So du is going to be derivative of secant theta is secant theta tangent theta. D theta. The reason I like u is secant, because then u squared minus 1 is secant squared theta minus 1 is tangent squared, right? Sine squared plus cosine squared is 1. That says tangent squared plus 1 is secant squared. So tangent squared minus 1 is secant squared minus 1 is tangent squared. Yes, I got this right. So this becomes bounds of integration change. First off, these weren't used, these were x's. I'm using x equals secant theta. X. So x equals 2 to x equals 3 corresponds to what theta value? When x is 2, that says secant theta is 2. That says cosine theta is a half. Do I know when cosine theta is a half? I do. That's at pi over 3 is the corresponding theta value. Do I know when x is 3? That's when cosine is a third. That's not one of the numbers on the unit triangle. So theta is going to be cosine inverse of a third, whatever that is. What's the function I'm actually integrating now? This might be a good time to just ignore these, do the whole integral, and come back and plug in 2 and 3 afterwards. But I'm going to do the substitution switch because I made a big deal about how it's the classy way of doing these. X squared minus 1 becomes tangent squared. I got tangent squared to the 3 halves becomes tangent cubed. dx is secant theta, tangent theta, d theta. One of these tangents cancels. I get secant over tangent squared. Uh-oh. This is an odd number of secants and an even number of tangents. That's usually the bad one. It's a negative even number, so that might mess things up. Maybe this isn't so bad if we rewrite it in terms of sines and cosines. Secant becomes 1 over cosine. Tangent is sine over cosine. That means 1 over tangent is sine under cosine, both squared. Oh, is this not that bad? This is cosine over sine squared. That's not bad at all. Huh, I was expecting this to be hard because of the even-odd thing. Maybe that doesn't work with a negative number. I'm going to let u be sine theta. Du will be cosine theta. I have one cosine sitting out here. This integral is going to turn into an integral of 1 over u squared du. Again, let's challenge the bounds of integration. When theta is pi over 3, what's sine of pi over 3? Sine of pi over 3 is root 3 over 2. When theta is cosine inverse pi over 3, I need to know what is sine of cosine inverse of 1/3. This is a rational, or this is an algebraic number. Don't write it like this. Do the reference triangle. If cosine, I'm thinking about what is the angle whose cosine is 1/3. I'm drawing a reference triangle where adjacent over hypotenuse is 1/3. That makes this one square root of 9 minus 1 is root 8. That's 2 root 2. So sine of this is opposite over hypotenuse is going to be 2 root 2 over 3. 2 root 2 over 3. Weird. This is what I need to integrate from. These are my bounds of integration. Integral of 1 over u squared, that's u to the negative 2. Integral of that is negative 1 over u. And evaluate that from root 3 over 2 to 2 root 2 over 3. I get negative 1 over root 3 over 2 is 2 over root 3 minus negative 3 over 2 root 2. Let's rationalize these denominators is the right way to do this. Stick a root 3 and a root 3 and a root 2 and a root 2. I'm getting, let's put this one first. 3 root 2 over 4 minus 2 root 3 over 3 is, I think, the right answer. Weird. That's not weird. That's it's an ugly number, but you know, it's a number. What's 27? Again, I'm doing work simplifying these numbers. Don't stress over doing this kind of work on a final. The number of points you're going to get for... Oh no, is this... Oh no, this is the last lecture. I don't need this note. I want... This note is the one I'm in the middle of. This is the one I'm saving. Cool. Here's number 27. We got to complete the square. I wish I had x squared plus 2x plus something that makes this a perfect square. What's the number that makes this a perfect square? I look at the 2, I cut it in half and square it. Half of 2 is 1, squared is plus 1. I don't get to put plus 1s just because I love them. I got to put a minus 1 also to cancel it out. This is the integral of the square root of x plus 1 squared minus 1. When I have x squared minus 1, that says the thing should be secant theta. I'm going to let x plus 1 be secant theta. Dx will be secant theta tangent theta. D theta. Because x plus 1 is secant, that means x plus 1 squared is secant squared minus 1 is that minus 1, that's tangent squared. Okay, I've written that enough times I think I can remember it for the rest of the day. This is the integral of square root of tangent squared is tangent. It's actually absolute value, but we don't have to deal with that. Times, what's dx? Dx is secant theta tangent theta. Uh-oh. I have an even number of tangents and an odd number of secants. This is the gross one. We start by doing parts. We're integrating tangent theta times secant theta tangent theta, d theta. I'm going to let u be the thing I want to take the derivative of as tangent. dv is going to be the other part, secant theta tangent theta, which is a good idea because I can definitely integrate that in my head. The integral of that is secant theta. du is going to be derivative of tangent is secant squared. I get uv is secant theta tangent theta minus the integral of v du is secant cubed theta. This is almost the original integral. I just have to change that secant squared into a tangent squared. This is secant theta tangent theta minus the integral of, that's secant theta times secant squared. Secant squared I'm going to write in the form of tangent squared plus 1. So my original integral, the integral of secant tangent squared is going to be secant theta tangent theta minus the integral of secant theta tangent squared minus the integral of secant theta. Move this to the other side. 2 my integral equals all that stuff. So my integral is half of that stuff. Half secant theta tangent theta minus half the integral of secant. The integral of secant is natural log absolute value secant plus tangent. But we still got to back substitute for what was theta. Remember, there was an original trig substitution before we had this big integral. This big trig substitution came from x plus 1 equals secant theta. So cosine theta is 1 over x plus 1. That's how I'll draw my reference triangle. Cosine is adjacent over hypotenuse is 1 over x plus 1. So this thing is going to be the square root of x plus 1 squared minus 1. FOIL that out, it's x squared plus 2x, just like the original problem had. So I get 1/2. Secant theta is x plus 1. Tangent theta is opposite over adjacent is root x squared plus 2x minus 1/2 natural log absolute value of secant theta is x plus 1 plus tangent theta is square root x squared plus 2x. You get this really elegant answer that has no trig in it at all. Feels so weird that this was mostly a trig problem. What was that one? That was 27. Let's do 29. Integrate this mess from 0 to pi over 2. Okay, I got a definite integral. Is there an obvious trig substitution? First off, the problem's messed up. This should have been a dt. I guess I want to let u be sine t, because there's a cosine out there. It's going to turn it into a trig substitution. I guess I could get ambitious and try and do that little u substitution and the bigger trig substitution all in one substitution. It's going to be sine t equals tangent theta. Let's do this the ambitious way. Let's say sine t is tangent theta is going to be our substitution. Derivative of this side is cosine t dt, which I have, that's nice, equals derivative of this side is secant squared theta d theta. Changing the bounds of integration is going to be a hassle. If t is 0, then sine t is 0, so tangent theta is 0, so theta is also 0. If t is pi over 2, that tells me sine t is sine pi over 2, that's 1. That tells me tangent theta is 1. That tells me theta is pi over 4. So this is theta equals 0 to pi over 4 is the new changed bounds of integration. I can do this in 2 steps, doing u equals sine t, and then doing u equals tangent theta. I'm being ambitious and doing them both in 1 step. In case you haven't seen how to do that before. That's like learning? Is it me being lazy or me being ambitious? I can't tell. What's our new bounds of integration? The point of this was that 1 plus sine squared t becomes 1 plus tangent squared theta becomes secant squared theta. So the square root of that becomes secant. Actually, it's absolute value secant, but actually secant's positive on here, so it doesn't matter. I get secant theta on bottom. Cosine t dt becomes secant squared theta d theta We're integrating secant. I know the integral of secant. It's natural log absolute value, secant theta plus tangent theta. We need to evaluate that from 0 to pi over 4. At 0, we get... Well, this is one of those places where I want to say at 0 you get 0, but I don't think that's true here. Let's do pi over 4 first. Natural log absolute value, let's just write it out. Secant pi over 4 plus tangent pi over 4 minus natural log absolute value secant 0 plus 0 plus tangent 0. Secant 0 is 1, tangent 0 is 0, natural log of 1 is 0. It is 0, the long way. What do you get when you plug in pi over 4? Natural log absolute value. Cosine pi over 4 is root 2 over 2, is square root of a half, so secant is just root 2. Tangent pi over 4 is 1. I got natural log square root 2 plus 1. That's an answer. 31. Oh man, this is the worst. We got to do completing the square, and it's the bad kind of completing the square where there's a constant on it. Let's do it. I guess let's factor out that 4. I got 3 plus 4 times. Let's factor out a negative 4. Let's make it 3 minus 4. So I can write it in the normal order. I get x squared minus x, right? And then I'll leave the blanks. Take this number, cut it in half and square it. Half of 1 is a half. Square that, you get plus a fourth is what I want. Minus a fourth is what I'm stuck with to deal with that. This stuff, I want to stay inside the parentheses. This stuff is going to come out of those inner parentheses. This becomes integral of x squared over 3 minus 4 times x squared minus x plus a fourth minus negative 4 times negative a fourth is plus 1, all to the 3 halves. So, okay, this is x squared over 4 minus 4 x minus 1 half squared, all to the 3 halves. I guess I can factor this 4 out of the big parentheses now. 4 to the 3 halves is going to be 2 cubed is 8. This is 1/8 integral of, now it's just 1 minus x minus a half squared, all to the 3 halves. Okay, this is ready for a trig substitution. I'm going to let x minus a half be, it's either sine or cosine. I'm going to make it sine theta, yes, because cosine is positive on the region when you need a full cycle of sine. That makes 1 minus x minus a half squared is going to be 1 minus sine squared. It's going to be cosine squared. And it means dx is going to be cosine theta d theta. So this becomes 1/8 integral of x squared is sine theta plus a half squared. We're going to have to FOIL that out in a second. Over, so I'm getting a messier numerator but a cleaner denominator, and that's usually worth it. Over 1 minus blah squared is cosine squared to the 3 halves becomes cosine cubed. Technically absolute value, but this is going to be positive on the region we care about. So, I get 1/8 integral of, FOIL that out, sine squared theta plus sine theta plus 1/4 all over cosine cubed. Well, the middle one's easy. Let's pull that one off. Sine theta over cosine cubed theta. Know how to do that one. Sine squared over cosine cubed. What is that? Secant tangent squared? That shouldn't be that bad. One fourth of 1/8 is 1 over 32. Integral of 1 over cosine cubed. That's secant cubed theta. That one's bad. I get 1/8 integral. This one I'm going to let u be cosine theta. du is going to be negative sine theta d theta. So I get negative integral 1 over u cubed. Integral of 1 over u cubed, that's u to the negative 3. The integral of that is going to be negative 1/2 will be positive 1/16. U to the negative 2. What was u? U was cosine, so this will be secant squared. Okay, check. That one's done. Plus, what's this one? This one is, I guess I'll write this one out. Sine over cosine is tangent. I can take 2 of those. The leftover 1 over cosine will be a secant. Gross. This is also an odd number of secants and an even number of tangents. This is just gross. There should be a way to smush this together with the other one somehow. I'm just not seeing it. That's how we smush it together. Okay, I'm going to rewrite that sine squared as 1 minus cosine squared. Yeah, that makes it way easier. 1 minus cosine squared theta over cosine cubed theta d theta plus 1 over 32 integral secant cubed theta d theta. This is 1 over cosine cubed is going to be 1/8 another integral of secant cubed. Still gross, but I can smush it in and only have to do the same problem once. Minus 1/8 cosine squared over cosine is just 1 over cosine is I'm integrating secant. I know how to integrate secant. So I'm getting 1/16 secant squared theta minus 1/8 integral of secant theta is natural log absolute values secant theta plus tangent theta plus 1/32 plus 1/8 is 5 over 32 integral of secant cubed theta. Do I do the integral of secant cubed? I guess this is what I'm getting paid for. Let's do it. To integrate secant cubed, I want to do this by parts. I want to let u be 1 secant theta. dv will be secant squared theta d theta. du is secant theta tangent theta. You know, I'm going to run off to a separate sheet of paper and integrate secant cubed so that I can pull this off. Sorry, I just noticed my mic was on mute for a while. Square that, you get 4 over 16 is a fourth. Over square root, the square root's gone. 5 over 64. Let's go ahead and put the 2 in, so that's 5 over 32. Times 2x minus 1 over, again, 2 square roots makes it just 3 plus 4x minus 4x squared. Minus 3 over 64. Natural log absolute value. That's 2x plus 1, right? Man. Plus a constant. This is one of those ones where I'm kind of tempted to take a derivative and see what the answer is, but I got too many more problems to get done tonight. See how all that miraculously... Like, the weird thing is all the square roots are actually gone, right? The original has a power of 3 halves there. Here there's no square root anymore. Here there's no square root anymore. Here there is, but if I split that up with the rule of logs, I could rewrite it without the square root. I guess the square root would come back after I took the derivative, though. Cool. Let's see, that was the last trig substitution one, right? Okay. Let's oh, here we go. Partial fractions. Let's mix this up. Do some factoring. I can factor an x out. I'm left with x squared minus 8x minus 15. Can I factor that? I want numbers that multiply to give negative 15 and add to give negative 8. Oh, these don't. It looks like it should be 5 and 3, but it's not. That would be negative 5 and positive 3. That would be minus 2, not minus 8. Oh, man. This is just x squared minus 8x minus 15. I don't think that... Nope, don't factor. Okay. Looks like I'm going to be completing this. Oh, yeah, that's almost ready to complete the square. Okay. Shoot, let's do it. X minus 7 over x squared minus 8x minus 15. It's going to be a over x and bx plus c over x squared minus 8x minus 15. Cross multiply. X minus 7 is a x squared minus 8x minus 15 plus bx squared plus cx. That's only hitting the x. So x minus 7 equals, I guess I should have said out loud, is the top smaller than the bottom? Yes, it was. How many x squareds? A plus bx squareds. How many x's? Negative 8a plus c x's. What's my constant? Negative 15a. What's my system of equations? A plus b's got to equal 0. Negative 8a plus c's got to equal 1. Negative 15a's got to equal negative 7. So a is going to be 7 over 15. B is going to be negative 7 over 15. C is going to be 1 plus 8a. That's going to be... I don't want to do 1 plus 8a. I guess I got to do 1 plus 8a. It's going to be 15 over 15 plus 8a is 56 over 15. That's going to be 71 over 15. Okay, now we just have to integrate this. Jeez, gross. A is 7 over 15 over x plus, what's b? B is negative 7 over 15 x plus, what's c? 71 over 15 over x squared minus 8x minus 15. This part I can integrate. This one's going to need a I got to complete the square on the bottom to do a trig substitution. And that's not going to be any fun either. That's x squared minus 8x. I wish I had a plus 16. Was it a minus 15 or a plus 15? It was a minus 15. I wish I had a plus 16, so I get a minus 31? Oh man, there's no way I put this problem right. If you're watching this in summer 2020, this must have been... Yeah, I'm not going to do this. This is a nightmare. I'm going to do the problem that I'm pretty sure I meant to write down, which was to have a plus there so the thing factors. I've done enough completing the square tonight. If you completed the square, I'm sorry I made you do it again. Cut that. You know what? Before I forget, let me also... put in... Where's my Technic Center? Technic Center. Let me change the problem so that I don't try and make someone do this next year. I don't want to work on a project. Backspace. Plus. Now it's a plus 15. And now it's x minus 5, x minus 3. Save. Let's compile that. I don't need you. Do I need you? There we go. Now it's a plus, and it factors. Ta-da! Again, 2020 students, sorry to put you through that. If you got through that. Minus 8x plus 15. Now it factors. It's going to be x minus 3, x minus 5. Yeah. It's going to be a over x, b over x minus 3, c over x minus 5. I'm going to do this with the cover-up method. If I multiply by x, then all this stuff goes away. When I plug in 0, I get a is negative 7 over negative 3 times negative 5. A is negative 7 over 15. What's b? To get b with the cover-up method, I want to multiply both sides by x minus 3, and then plug in 3. That'll clear all that stuff out. B will be what I get when I plug 3 into this thing. Plug 3 into that, and I get negative 4 over 3 times negative 2 is negative 6. That's 2/3. Now let's get c. I'm going to multiply both sides by x minus 5, then plug in 5. That'll clear all that out. C is going to be, what do I get when I plug 5 into that? C is going to be negative 2 over 5 times 2, 10. That's a fifth. Is it crashing? I feel like this thing's about to crash. Oh, is it just my stylus acting up for the first time in a while? I'm now trying to integrate negative 7/15 over x, 2/3 over x minus 3, negative 1/5 over x minus 5. I can do that. It's negative 7/15 natural log absolute value x plus 2/3 natural log absolute value x minus 3 minus 1/5 natural log absolute value x minus 5 plus a constant. I've seen calculus textbooks that go nuts and smush this all together in one natural log. The rules of natural logs lets you put these up as exponents and then multiply, divide these things. So you can rewrite this as natural log of x minus 3 to the 2/3 over x to the 7/15, x minus 5 to the 1/5. And you can write it like that if you're a psychopath, but I think this is the normal way to write it. Let's do 35. Clipboard. I can factor in x out of that denominator. 1 over x cubed plus 2x is going to be 1 over x squared plus 2. I want you to be a over x and... come on. And... wait, it's just here you don't work? And bx plus c over x squared plus 2. If I clear the fractions out by multiplying both sides by x and by x squared plus 2, I'm getting that 1 needs to be a x squared plus 2 plus bx plus c x. This is how many x squareds, how many x's, what's my constant? The number of x squareds is a plus b. How many x's do I get? I get c, and that's it. What's my constant? My constant is 2a. And this needs to equal 0x squared plus 0x plus 1. So I want a plus b is 0. I want 0 is c. That's nice. I want 2a is 1. So a is a half. B is negative a half. C is 0. The c being 0 is nice because I don't have to do the tangent inverse one that you need to do for that. This integral now turns into the integral of 1/2 over x minus 1/2 times x over x squared plus 2. Hey, look what I do here. I'm going to change that to 1/4 of 2x. And now I'm ready for u equals x squared plus 2 du is 2x dx. This first integral is 1/2 natural log absolute value x. The second integral turns into minus 1/4 integral 1 over u du. So this turns into half natural log absolute value x minus 1/4. Natural log absolute value u is x squared plus 2. Oh wait, x squared plus 2 is positive, so I don't need the absolute value on this one. Plus a constant. Partial fractions. 37. So we want x squared over, so is the top smaller than the bottom? Bottom's cubic, top's quadratic, yes. Over x plus 1 cubed is going to be a over x plus 1, b over x plus 1 squared, c over x plus 1 cubed, and that's it. The cover-up method could get me c. I'd have to multiply both sides by x plus 1 cubed, plug in negative 1. If I do that, that's going to tell me that c should equal 1, I think. I'm plugging negative 1 into this. Yeah. I'm just going to use that as a check at the end, though. Multiply both sides by everything. I get that x squared should equal a x plus 1 squared, b x plus 1 c. So x squared should equal a times x squared plus 2x plus 1, bx plus b plus c. This is some x squareds and some x's and a constant. How many x squareds is? Just a. How many x's? 2a plus b. What's my constant? It's a plus b plus c. It's like an interesting triangular one. This is supposed to be equal to a squared, so a should equal 1. Nice. 2a plus b should equal 0. That immediately gives me 2 plus b is 0, so b is negative 2. Nice. A plus b plus c should equal 0. A plus b is negative 1, so c should be 1. Nice, and that confirms what we did. Great. Great. Our integral turns into the integral of a is 1 over x plus 1. B is negative 2 over x plus 1 squared, that's a power of negative 2, plus c is 1 over x plus 1 cubed, that's a power of negative 3. I get natural log absolute value x plus 1, add 1 to the exponent, I get plus 2, x plus 1 to the negative 1, plus add 1 to the exponent, you get negative 2, divide that, you get negative 1/2. X minus 1, x plus 1 to the negative 2, plus a constant. X plus 1 is a baby substitution. This works. I think it's worth noting that u equals x plus 1 is also a good substitution that makes it into something you don't have to do partial fractions on. You have to FOIL a quadratic on top, that's as bad as it gets. I didn't notice it till afterwards, though. Also, the instructions say find the partial fraction decomposition, so that's like the bigger point of the problem. 39 is this. Clipboard. Pasteboard. Ooh, this is going to be gross. Is the top smaller than the bottom? Bottom, when I square that, it's going to give me an x to the 4th, with the extra x is an x to the 5th. So yes, the top is smaller than the bottom. I want 5x to the 4th plus 2 over x squared plus 1 squared should be a over x, b, x plus c over x squared plus 1, d x plus e over x squared plus 1 squared. We get a 5 by 5 going. Sound the alarm. I can find x with the cover-up method. If I multiply both sides by x, and then plug in 0, all this goes away. And I'm left plugging 0 into the left-hand side here, and I get 2 over 1, so we should end up with a is 2 over 1. I can't get all the letters, so I'm just going to use this as a check. At the end, I'm hoping to end up with a equals 2. That looks like it's clear. Yeah. I didn't do this in lecture, at least not in summer 2020, but I feel like going ahead and showing off how dumb the cover-up method is with these complex things. The thing I'd like to do is multiply both sides by x squared plus 1 squared, and these guys will have an extra x squared plus 1 on them, and then plug in something that makes x squared plus 1 0. That thing is I. Let's try that out and see what we get. If I multiply both sides by x squared plus 1 squared and plug in x equals I, I'm plugging I into the left-hand side. I'm getting 5i to the 4th plus 2 over I needs to equal di plus e. What's I to the 4th? Think about it for a second. I squared is negative 1. Square that again, you get 1. I to the 4th is 1. So this is 7 over I. Needs to equal di plus e. That's negative 7i equals di plus e. You know how every complex number can be written in the form a plus bi? That's kind of what's going on with my di plus e. I know that d and e have to end up being real numbers, so I see the real part and the imaginary part here. E has to be 0, and d has to be negative 7. I believe I have worked out that e better be 0, and D better be -7. Again, I'm not able to get all the letters with the cover-up method, so I'm going to end up doing the whole multiplying everything out. But that's what it's like when you're plugging in these i's. Usually this isn't worth covering in the main class, but I can show it off here. Let's try this out now. Let's clear the denominators. 5x to the 4th plus 2 needs to equal. What do I need to multiply a by? I need to multiply a by x squared plus 1 squared. What do I need to multiply bx plus c by? If I'm clearing denominators, I'm multiplying by x and x squared plus 1 squared. You've got an x squared plus 1 squared. One of the x squared plus 1s cancels with what's on bottom. You're getting multiplied by x squared plus 1. I might as well FOIL that out. That's x cubed plus x. What's dx plus e getting multiplied by? That one's way easier. You're just getting the leftover x because you have the most canceling of all. Okay, this is going to be a times x to the 4th plus 2x squared plus 1. This is going to be bx to the 4th. Outside is bx squared. Inside is cx cubed. Last is cx. You're going to be dx squared plus ex. Let's group by powers of x. I'm going to have some x to the 4ths. How many x to the 4ths? A, check, plus b, that's it, x to the 4ths. How many x cubeds? C, is that it? That's it, c x cubed. How many x squareds is? 2a. It's easy to forget the a needs to come into here. Keep in mind everything here should have an a or a b or a c at the end. How many x squareds is 2a plus b plus d? X squareds is. How many x's? C plus e x's. C plus e x's. What's my constant? Oh, did I? Yeah, I got the dx squared here. Did I get the cx cubed? I got the cx cubed. My constant is a. Did everything go right? Yeah, I got that. I think I hit everything. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. I had 1, 2, 3, 4, 5, 6, 7, 8, 9 terms before, so I think we got everything. 5x to the 4th plus 2. So I need 5 equals a plus b. C is the x cubed. There's no x cubes. 2a plus b plus d needs to be how many x squareds is. There's none. C plus e needs to be how many x's. There's none. A needs to be the constant is 2. I had a was 2. Okay. C is 0. Combine that with that and I get e is 0. A plus b is 5, so b better be 3. D needs to be negative 2a minus b. What's negative 2a is negative 4 minus 3 is negative 7. Hey look, d was negative 7 over here. E was 0, a was 2. Everything we predicted from the cover-up method has come true. This feels good. What am I integrating now? I need to integrate. A was 2. 2 over x. Bx plus c is 3x plus 0, so just 3x over x squared plus 1. Dx plus e is negative 7x plus e is 0 over x squared plus 1 squared. These aren't that bad to do. Here I want u to be x squared plus 1. Here I also want u to be x squared plus 1. We didn't have the other parts, so these things, when you have an extra x on top, it's an easy substitution. When you don't have the extra x on top, you're doing the integral of 1 over x squared plus 1 is tangent inverse. If it's squared, you're probably doing the trig substitution, x equals tangent theta, but it works pretty easily. It's not a bad trig substitution to do. If you have x squared plus something else, now the trig substitution's a little work and life's a little grosser. Cool. Can I do this in my head? I'm going to put a 3/2 out here to make that a 2. So now I'm integrating 1 over u. I'm getting natural log u. Let's make it minus 7 over 2. Now I get a 2. Now it turns into the integral of u to the negative 2. That's going to be negative 1 over u. Whew. There we go. Cool. We're still going. That was 39. 41. We're just stating the form of the partial fraction decomposition. Is the top smaller than the bottom? The top is cubic, the bottom is a nightmare. So yes, the top is smaller than the bottom. Have we factored the bottom as much as we could? We can pull a 2 out of this and get 2x plus 1/2. Does anything else in sight have a root at negative 1/2? No, I don't think it does. This thing doesn't factor at all. This thing factors into x minus 1, x plus 1. Oh hey, I have x minus 1s over here. That's a big deal. I need to factor that. Okay, so let's factor this thing before we try and do anything. This is x cubed minus 3x squared plus x plus 2 over x cubed, x squared plus 1 to the 4th. X squared minus 1 squared is going to be x minus 1 squared with another x minus 1 squared makes x minus 1 to the 4th, x plus 1 squared. 2x plus 2 squared. 2x plus 1 squared. If it was 2x plus 2, that would be an x plus 1. I'd have to mush them together. Okay, these are ready to go. This is going to break up into a over x, b over x squared, c over x cubed, dx plus e over x squared plus 1, fx plus g over x squared plus 1 squared, hx plus I over x squared plus 1 cubed. Still going. Jx plus k over x squared plus 1 to the 4th. L over x minus 1, m over x minus 1 squared, n over x minus 1 cubed. I'm skipping O because it looks too much like 0. P over x minus 1 to the 4th. Q over x plus 1, R over x plus 1 squared, S over 2x plus 1, T over 2x plus 1 squared. That's it? That's it. Boom. Whew. Whew. Make it clear, you're not actually finding the decomposition. We're just stating the form. Oh, and we're at improper integrals. Oh no, there's more integrals after this. We're almost done. I need to evaluate this improper integral, say if it converges. Is anyone watching me? Nobody's watching me. This thing's undefined at 5. At 5, this thing goes to infinity, so I'm not allowed to integrate it directly to 5. I need to integrate it to something else, and let that something else approach 5, and in particular, approach it from the left. 1 over 5 minus x to the 1/3. This is the limit as b approaches 5 from the left of, I can do that integral. That's 5 minus x to the negative 1/3. I'll get 5 minus x to the positive 2/3, divide by 2/3, 3/2, divide by the x coefficient, negative 3/2. Now evaluate that from 0 to b. This is going to be negative 3 halves 5 minus b to the 2/3 minus negative 3. Why'd you do that? Minus negative 3 halves 5 minus 0 to the 2/3. Can I take this limit as b approaches 5 from the left? Yes, this thing is defined at 5. You can raise 0 to a positive exponent. The negative fractional exponent, when you integrate it, becomes a positive fractional exponent. You can evaluate that at 0. Plug in 5, you get 0. This equals, I don't need L'Hopital's rule or any goofy tricks. This equals 0 plus 3 halves 5 to the 2/3. It converges to 3 halves. What is that? Cube root 25. Cool. What's up next? 45. Integrating r log r. This likes parts. I want u to be natural log r. Du is derivative of that is 1 over r dr. Oh, actually, the whole point of the problem is not about parts. I need to rewrite this. This is the limit as a goes to 0 from the right. Log has a pole at 0. This is undefined at 0. I need to take a limit as a approaches 0 from the right of the integral from a to 1 of r log r dr. Now I do the same parts. dv is going to be r dr. Oh, v looks too much like r when I write it. v. So v is half r squared. This is going to be the limit as a approaches 0 from the right of uv becomes half r squared ln r evaluated from 1 to a minus the integral from a to 1 of v du is half r squared times 1 over r. R squared times 1 over r is r. That integral I can do. Plug in 1, you get 0. Yeah, natural log 1 is 0. Minus half a squared natural log a. Minus, integrate this, you get a 4th r squared evaluated from a to 1. This is all still inside the limit. It's the limit as a goes to 0 from the right of 1/4 of 1 is 1/4 minus a 4th a squared minus half a squared natural log a. I can do most of these limits. This one's a 4th. This one is 0. So the question is, can I do the limit as a goes to 0 from the right of a squared natural log a? The traditional way to do this limit is write it as log a over 1 over a squared and do L'Hopital's rule. I'm one of those teachers who thinks you should really do L'Hopital's rule. When you do L'Hopital's rule, you should say you're doing it and what version of it. When you try to plug in 0, you get infinity on top and infinity on bottom. So this is the infinity over infinity version of L'Hopital's rule. Hey, by the way, there's a million different ways we could have defined the derivative. Instead of talking about the slope, we could have been talking about the angle. We could have been talking run over rise. There's lots of different ways of measuring ideas like slope. So we could have had lots of different ideas for derivatives. It is an absolute goddamn miracle that L'Hopital's rule turned out to be the simplest possible version of the formula, and it's the same formula for 0 over 0 as it is for infinity over infinity. It cannot be understated how simple L'Hopital's rule is to remember for what a crazy rule it is. Okay, that's me done talking. This is a fourth minus a half. Now it's the limit of 1 over a over negative 1 over a cubed. What do you get when you plug this into 0? This is the limit as a approaches 0 from the right of negative 1 over a to the fourth. That's 1 over 0. That's undefined. It's actually negative infinity with that minus is plus infinity. I can say the integral diverges. To plus infinity. Is it plus infinity? It should be minus infinity. Why is it not negative? Because log r goes to negative infinity. The log is negative at a small positive number. There's a minus here, there's a minus here, and a minus here that's making it positive. Like, this is the only important part. That other part is finite. That's not the issue. It's this limit. I'm thinking it should be negative. Why is that minus there? UV I'm not going crazy, right? What does r log r look like? What? The function's defined at 0. This isn't even undefined then. What is going on here? Why did I do this wrong? Did I do this limit wrong? Log a over 1 over a squared. Log a goes to infinity. 1 over 0 squared goes to infinity. Derivative of the top, derivative of the bottom. Oh, that's what I'm doing wrong. I reduced the fraction wrong. A over a cubed isn't, there's not more a's on bottom, there are more a's on top. I'm getting 1/4 minus 1/2 limit as a goes to 0 from the right of negative a squared. Now when I plug in 0, I get 0. The integral converges to 1/4. Okay. This is maybe not even an improper integral, because the function actually does have a limit at 0. It's just sort of the sort of thing where it's not... To check that the function does have a limit at 0 is the same type of computation you're doing. Yeah. Okay, let's do number 7. Here we go. Now we're into the all mixed up problems. There are many ways to do these. These problems I put in this list should all be things that have many interesting ways to do them. I'm going to jump to what I happen to know is the slickest way of doing them. I'm going to factor a square root x out of the bottom. I get square root x times root x plus x. I'm going to do the substitution u equals root x. So x is u squared. So dx is 2u du. This turns into the integral of dx is 2u du. Root x is u. That's u plus u squared. Factor out another u. Or one of these cancels. 2 over u plus 1. This is a baby partial fraction. It's going to be a over u, b over u plus 1. Cover up method. Multiply by u, plug in 0, get a is 2. Multiply by u plus 1, plug in negative 1, b is negative 2. 2 over u minus 2 over u plus 1. This is natural log absolute value u times 2 minus 2 natural log absolute value u plus 1. I get 2 natural log absolute value u was root x minus 2 natural log absolute value root x plus 1. The 2 cancels with the square root here. This is just natural log x plus c. I get natural log x minus 2 natural log root x plus 1 plus a constant. Root x plus 1 is only positive, so I don't need the absolute values. Are we close to done? Oh, we got a ways to go. But I can feel it. 1 over 1 plus e to the x. I love this integral. There's so many ways to do it. The most obvious, if I do the substitution u equals e to the x, x equals natural log u, you end up with something that you can do a little partial fraction on. That works. I like adding e to the x and subtracting e to the x. Kind of does the partial fraction from here. You get integral of 1 minus e to the x over 1 plus e to the x. To use the u substitution, u equals 1 plus e to the x here. I get integral of u is just x, integral of 1 is just x. This integral after the substitution becomes the integral of u du. No, 1 over u du. So I get x minus natural log absolute value. U was 1 plus e to the x. Hey, wait, I don't need these absolute values because e to the x plus 1 is positive. That step doesn't matter. It's not like there's a shortage of absolute values. But I like to pretend there's a shortage of absolute values anyway. Here's 51. I guess I want to try the substitution u equals e to the x, or maybe e to the x plus 1. E to the x plus 1 looks better. I can soak up the plus 1 while I'm doing this. So du is going to be e to the x dx, and x is going to be natural log u minus 1. This turns into the integral of this thing is natural log u minus 1. These two things are du. That thing is square root u. The du is already there. What am I looking at here? This is the integral of natural log of u minus 1 times u to the negative 1/2. I love parts for natural logs. Let's try parts. Parts, when you already have your problem written in terms of u's, is gross. I like using a capital U and a capital V for my parts now, because lowercase u is taken. U is going to be the thing I want the derivative of, natural log u minus 1. Du is going to be 1 over u minus 1. V is going to be u to the negative 1/2, so That's dv. So v is going to be u to the 1/2, divide by that. Yeah. This becomes uv is 2 root u natural log u minus 1 minus the integral of v du is 2 root u over u minus 1. Still gross. I guess I want to try a substitution to get rid of the square root. I'll let v equal root u. So u is v squared. So du is 2v dv. This becomes 2 root e to the x plus 1. Natural log u minus 1 becomes just x, so that thing is all there. Minus 2, new integral is v over v squared minus 1. du is 2v. So this is what you end up with. I get minus 4 integral v squared over v squared minus 1. This is ready for, this is a rational function. I can do a partial fraction decomposition on it. It's going to start with long division. Instead of writing out the long division, I'm in that same situation as that e to the x thing, where if I put a minus 1 plus 1, that kind of does the long division. I get stuff minus 4 integral of 1 plus 1 over v squared minus 1. I get stuff minus 4v minus, or let's write that plus the integral of negative 4 over v squared minus 1 dv. I want negative 4 over v squared minus 1 dv to be a over v minus 1, b over v plus 1. Cover-up method will do everything here. Multiplied by v minus 1. I guess I should write out the FOILed version here for the cover-up method to work. V minus 1, v plus 1. Multiply by v minus 1, plug in 1. A is negative 4 over 2. A is negative 2. Multiply by v plus 1, plug in negative 1. Get negative 4 over negative 2. B is positive 2. I get stuff minus 4v plus the integral of negative 2 over v minus 1 plus positive 2 over v plus 1. I still need to substitute this v, but I get stuff minus 4v minus 2 natural log v minus 1 plus 2 natural log v plus 1 plus a constant. What was v? V was root u. What was u? U was e to the x plus 1. So it was root e to the x plus 1 is v. I get, what was this stuff I've been just scribbling? 2 root e to 2x root e to the x plus 1 minus 4 root e to the x plus 1 minus 2 natural log absolute value root e to the x plus 1 minus 1 plus 2 natural log parenthesis root e to the x plus 1 plus 1. This one's all positive, so oof, oof. Oh my gosh. Whew. Oh, that's a rough one. I used a bunch of tricks. 51. Cool. 53. I got a definite integral, integrating sine inverse from 0 to positive half. Sine inverse loves parts, because its derivative isn't sine inverse anymore. U is going to be sine inverse. dv is going to be, everything else is just dx. du is derivative of sine inverse is 1 over root 1 minus x squared dx. V is the integral of that is x. I get uv is x sine inverse x evaluated from 0 to a half minus the integral from 0 to a half of x over root 1 minus x squared. Plug in 0, you get 0 times 0. Plug in a half, you get a half. Sine inverse of a half, when does sine equal a half? That's at pi over 6. Minus. This integral we can do by substitution. Let u be 1 minus x squared du will be negative 2x dx. I wish I had a negative 2. Well, I got the negative. I'll put the 2 and a half. So I get this plus 1 half. New integral is u to the negative 1 half du evaluated from new bounds of integration are 1 to 1 minus a half squared is 3/4. So this is pi over 12 plus 1 half. Integral of that is root u to the 1 half times 2. It's just u to the 1 half. The 2 goes away, yeah. Or the 2 cancels with that 1 half. Yeah, so it's just u to the 1 half needs to be evaluated from 3/4 to 1, or from 1 to 3/4. I got pi over 12 plus root 3 over 2 minus 1. Cool. Oh man, you guys do not, I don't recommend doing all the homework in one night. The hard one's secant cubed. It's hard if there's an even power of tangent and an odd power of secant. Well, neither of those is true. This should be easy in 2 different ways. You might want to do the substitution u equals 4x if you really hate those 4s. I'm going to try and just suck it up and deal with the 4s being there. I can pull off a secant tangent, or I can pull off a secant squared. Let's pull out a secant squared. I think that'll be a little bit easier. Seeing that secant squared makes me know I want to try u equals tangent 4x, because then du will be secant squared 4x dx times 4. I wish I had a 4. I'll stick in a 4 and pop out a 1/4 to eat it up. If my u is tangent, well then that's going to be u to the 5th. What's this going to be? I know a relationship between sine squared and between secant squared and tangent squared, if I can only remember it. Sine squared plus cosine squared is 1. Divide both sides by cosine squared. Tangent squared plus 1 is secant squared. Secant squared is tangent squared plus 1. That's u squared plus 1. Even with the 4. I get 1/4 integral u to the 5th u squared plus 1 du. Don't say this is 1/6 u to the 6th times 1/3 u cubed plus u. Don't do that. You can't integrate a product factor by factor. Unless one of the factors is a constant, that doesn't work. This is the integral of u to the 7 plus u to the 5th. That's going to be 1/8 u to the 8 plus 1/6 u to the 6th plus a constant. I'm getting 1 over 32. U to the 8 becomes tangent to the 8. 1/6. What's u to the 6th? That's tangent to the 6th, 4x. We're really flying now. We got past the partial fractions. How long have I been doing this? 2 hours. Hot diggity dog. Let's see, we just did 55, so we're on 57 now. I got the simple denominator, but I don't know how to smush that top in with it. This is, not obvious. I guess I'm going to try a substitution that gets rid of the square root. What happens if u is root x minus 4? So u squared plus 4 is x. So dx is 2u du. Does that do anything? Get the integral of... Now I have a simple top and a messy bottom, which is usually worse. Times dx is 2u squared. Or it's 2u with the u that's already there. It becomes 2u squared. That's not so bad. If I pull the 2 off, I can put the plus 4 minus 4 thing. That's 2 integral 1 minus 4 over u squared plus 4. 2 integral of 1 is 2u minus integral of 8 over u squared plus 4. Okay, this is ready for a trig substitution. You can let u equals 2 tangent theta. But this is basically a smaller substitution of, this is almost u squared plus 1. It's a baby substitution. It's the kind of baby substitution that, like, I have this memorized. I think I'd recommend memorizing this one. The integral of 1 over x squared plus a squared is 1 over a tangent inverse x over a. Just do the chain rule and you'll see how you get the right thing. Or the derivative of that is 1 over a. What's the derivative of that? It's 1 over x over a squared plus 1. Chain rule spits out another 1 over a. You get a 1 over a squared. Foil that in, you get x squared plus a squared on the bottom. This is, I think this shows up enough, and trig substitution is painful enough that it's worth memorizing this to avoid a little trig substitution. Your call. It's 8 times 1/2 tangent inverse u over 2. What was u? U was root x minus 4. So I get 2 root x minus 4 minus 4 tangent inverse root x minus 4 over 2 plus a constant. Whew. 59. We got a cinch. We got a cosh. Oh my gosh, it's a cinch, you guys. Cosh and cinch basically work like sine and cosine for most integration purposes. The only difference is their derivatives are each other without a minus sign. If I had e to the 2x cosine 3x, I know I want to integrate it by parts twice and get back the original and then move that to the other side and divide. We did an example just like that earlier. Where was that? It was when we first hit parts. Yeah, this one. You integrate it by parts twice, move to the other side, divide by a constant. I've already done one very similar to this. Instead of doing that thing again, I mentioned at the time that it might be a slicker way around this is to just say, well, when I do this, I know the answer is going to be some multiple of e to the 2x cosh 3x plus some multiple of e to the 2x sinh 3x. There's nothing special about the sinh cosh thing. If it was a sine or a cosine, this would work just as well. The difference is going to be a minus sign that's not obvious what it is. It's maybe not a bad idea. I'm going to do this another way after this. This feels cheating to say I know the answer is going to be basically this, I just need to know the constants. But when you get to a differential equations class, a lot of that stuff is, I know the answer is basically this, I just need the constants. So this feels like warming you up for the next big class you have. When I take the derivative of the right-hand side, I get product rule. Derivative of the first, 2a e to the 2x, leave the second part alone, cosh 3x, plus leave the first part alone, a e to the 2x, derivative of the second. Derivative of cosh is just sinh. So derivative of cosh 3x is sinh 3x times 3. Now to do the derivative of this, also product rule. Derivative of the first is 2b e to the 2x, leave the second part alone, sinh 3x, plus leave the first part alone, b e to the 2x, derivative of the second. Derivative of sinh is just cosh 3x times 3 from the chain rule. I want this to equal e to the 2x cosh 3x. I do something kind of like when I do the partial fraction decomposition. Did I get some e to the 2x cosh 3x's? Yes, I did. I got this and I got this. So I want 2a plus 3b to be 1, because I want to end up with 1 e to the 2x cosh 3x. But I also got this stuff that I didn't want. So I want 3a plus 2b to equal 0. Like, these are like terms. I have 2a plus 3b e to the 2x cosh 3x plus 3a plus 2b e to the 2x cosh 3x. And my answer is supposed to be 1 e to the 2x cosh 3x and 0 e to the 2x sinh 3x. So I'm figuring out the a's and the b's that make this equal. I'm getting around doing an integration by parts. What does this tell me? This tells me b is negative 3 halves a, stuff that into the top line, 2a plus 3 times negative 3 halves a equals 1. So 2a minus 9 halves a better equal 1. 4 minus 9 is this, wait, yeah, this is negative 5 halves a equals 1. So I think a is going to end up being negative 2/5. Is that right? I believe it is. So b is negative 3 halves a. Negative 3 halves times negative 2/5 will be positive 3/5. A is negative 2/5, b is 3/5. I've got an answer. My answer is negative 2/5. I mean, I said my answer was this. I just didn't know a and b. Now I know the a and b. Let's cheat and make a tiny little extra space. So the integral is a negative 2/5 e to the 2x cosh 3x plus 3/5 e to the 2x cosh sinh 3x plus a constant. You can only really do this if you've done this the right way by parts a couple times and then taken the derivative and seen, I see how it goes. These things are going to cancel out. These numbers happened to be the right numbers where this thing ends up being 1 and this thing ends up being 0. And I know how to figure out the numbers so that this thing ends up being 1 and this thing ends up being 0, because I had a section on systems of equations in some pre-calc class in my life. There's one way at it. Here's another way at it. If you just use the definition of cosh, this all evaporates, I think. I forgot that. I didn't notice that till I was already committed to doing the whole parts thing twice. What's cosh 3x? Cosh is e to the... Cosh x is e to the x plus e to the negative x over 2. So cosh 3x is e to the 3x plus e to the negative 3x over 2. Yeah, you distribute this in. This is just e to the x's. This is a half e to the 5x plus a half e to the negative x. Yeah, this is seems easier. This is a 10th e to the 5x minus a half e to the negative x plus a constant. Man, yeah, okay. You don't need to use parts on this. 61. Looks like a trig substitution. Oh, this is the last one! Oh, you guys. I've been sitting in my closet for 2 hours, and I'm almost done. Oh, and my notes didn't crash. That means I can amend these if I mess them up. I want x to be root 3 tangent theta, because then x squared is going to be 3 tangent squared. X squared plus 3 is going to be that plus 3 is going to be 3 tangent squared plus 1 is secant squared. Right? There's no, like, if there was an extra x up top, I could just do a simple u substitution. It's not there. We're probably stuck with trig substitution. Dx is going to be root 3 secant squared theta, d theta. What's this going to turn out to? This turns into the integral of 3 plus x squared is secant squared is 3 secant squared to the 3 halves. Dx is root 3 secant squared theta, d theta. Secant squared to the 3 halves is secant cubed. 3 to the 3 halves is 3 root 3. So I got 3 root 3 secant cubed theta, root 3 secant squared theta, d theta. This is cosine, right? We're left with just 1 over secant. 1 over secant is cosine. I got the integral of 1/3 cosine theta. The integral of cosine theta is 1/3 sine theta. What's sine theta? Well, tangent theta was x over root 3. Should be, I'm drawing my reference triangle, opposite over adjacent is x over root 3. So this is the square root of that squared plus that squared is x squared plus 3. Sine theta will be opposite over hypotenuse. That'll be that over that, x over 3 root x squared plus 3, plus a constant. That's the odds from the exam 1 homework. I did that in what? 2 hours, 18 minutes, assuming the evens are just as long. This is like under 5 hours of homework. You can't complain about too much homework. I gave you 5 hours of homework. For 2 weeks, that's the right amount. Cool. Done video. Done. End stream. Publish.